All right, so let's quickly review of what we talked about in terms of the settlement of the soils. Remember, we talked about, in general, the stress-strain curve, right? In the stress-strain curve, you basically have two sets of curves associated with the level of compaction of the material. If you have loose material, you don't see that visible peak. If you are dealing with material that are well compacted, you see that the softening and hardening of the material will take place. You see the peak, and then you see the softening of the material. You basically use the stress at failure, and you call that the strength of the material. All right, so that's basically the general concept that we had for the stress-strain curves and the two types of stress-strain curves that we have. We know how to do the calculations of the stresses. What type of stresses are you familiar with? You know the geostatic stresses, right? The geostatic stresses are stresses associated with the weight of the layers of soils, right? So for that, all you need to know is the unit weight and the height of the layer, or thickness of the layers, right? How do we get the height of the layer? Simply you go and get that in the field based on the boreholes and the observation wells that we have. Now, for the unit weight, you get the material and you figure out what the weight is, what the volume is, and divide them by one another, you get the density of the material, and based on that you can calculate the unit weight. We also talked about the non-destructive test. Remember, we talked about the nuclear density gauge, and the nuclear density gauge was essentially a non-destructive test that you can use in order to get an indication of the density of the material, right? So you can get information about the density, you can figure out what are the layering of the soils are, and based on that information you can calculate the geostatic stresses. On the other side, you had the information about the stresses exerted by the weight of the structures, right? Remember, for instance, based on the information that you had from your LRFD or the ACI method, remember you had a U value, which was the weighted loads, right? Remember, you had the dead load, you had the live load, you had different coefficients that you can basically inflate the magnitude of the load to be able to essentially account for the uncertainties in the loading conditions. So you get that information and sum them up, and by sum them up, you're basically referring to superposition of the loads, right? So the superposition of principle is valid when you're looking at the linear system, and we talked about that. Talking about the linear or linear elastic systems, what kind of material are we dealing with in terms of material properties? We are dealing with material properties of elastic modulus and Poisson ratio to be able to define the behavior of the material. Therefore, you need only one elastic modulus and one Poisson ratio to be able to characterize your material. And by characterization, we mean that you can calculate the responses. That would be the stress-strain curve. And the other side, you can also get an indication of the deformation characteristics, and that's basically what we're targeting or what we're looking at. All right, so that's basically the general concept that we had behind the stress-strain curve. You figure out what the loading conditions are, load, light load, earthquake load, wind load, all that kind of loads, and find the coefficient and basically figure out what would be the total magnitude of load that is acting on the soil. Once you get that information, now the second step would be figuring out what is the strength of the layers, right? Because you want to place the foundation at the top of them. And stress and failure in the stress-strain curve, we call that the strength of the material. We had different ways to figure out what that number is. Remember, in the lab we had the direct shear test and we had triaxial tests, right? So based on that information, I can get the information about the strength properties. You had the stresses, you had the strength properties. Based on that information, that you can now calculate the settlement of the soil. And settlement, in very simple term, is that permanent deformation, plastic deformation that you see at the top of the soil. It's not specifically associated with the top layer. It's basically cumulative value in all of these different layers that we have. In reality, remember, we talked about soils are multi-layered, non-homogeneous materials, right? So you have different layers, meaning that you can have sandy layer at the top, you can have clay layer beneath that, you can have some other type of silty material beneath that. So depending on the layer configurations that we have, you essentially end up with different strength properties, right? And also with different settlement properties. That's also associated with the location of the groundwater table, right? Remember, we talked about the influence of the variation of the groundwater table and how that influences your effective stresses. And you know that the effective stress is an input parameter to the the strength equation. Remember, tau sub F was C plus sigma prime, effective stress times tangent of phi, right? So those are essentially how you can connect the dots when you want to figure out what are the strength properties, what are the stresses, and how you can calculate the deformations or settlement of the material, right? So that's what we talked about in previous lecture. Also, we talked about the different types of settlement that we have. Remember, we talked about immediate settlement, and we talked about time-dependent settlement. Immediate settlement is independent of time. Time-dependent settlement is obviously a function of time, right? Immediate settlement means as soon as I apply the load, the deformation will take place beneath the loading condition that we have. Oftentimes, we have vertical stresses or vertical loads, and the deformations are going to be also in vertical form. All right, so that would be the immediate settlement. What was the characteristic of that? There were two important things there, Julio. One of them was the layered elastic theory, or theory of elasticity, is valid. What that means is that you can use that E value and mu value that we talked about in order to calculate the immediate settlement. And remember that we talked about that settlement or immediate settlement, we call that S sub I was equals to Q, which is the distributed pressure on the surface, times B, which was the width of the loaded area, times I sub S. I would suggest that you take a look at that information, because if you don't review the material, you get lost in this part of the lectures. And then you have I sub S was the shape and rigidity factor that you can essentially figure that out from table 10.4 in your textbook, right? So that's what we had in the numerator, right? And times 1 minus mu to the power of 2, and it was divided by E, which was the modulus of elasticity. In very simple terms, it says that the higher would be the modulus of elasticity, the lower would be the immediate settlement. And that makes sense, right? The stiffer would be the material, the lower would be the settlement properties of the system. So that was how you can calculate the immediate settlement, and that's very simple and straightforward. But the second component that we had, which was the time dependency of the settlement, that was the one that is somewhat challenging, meaning that you have to figure out multiple parameters from different types of tests to be able to calculate the time dependent of the settlement. All right, so time dependency of the settlement has to do with the drainage, right? We talked about the dissipation of the core water pressure. In very simple terms, if you have a layer that is fully saturated, right? Fully saturated, how many phases do I have? Two, and those are? You have water and you have solid grains. Do you agree? Meaning that you don't have any air content in the soil. There is no air void traps, assuming that in the soil situation that we have. All right, so how do you calculate the E value, or the void ratio? Yes, you do have the volume of voids divided by all right, so let's think about that here. You have E, which is, do you agree with this equation? So you have volume of voids over volume of solids. Can you decompose volume of voids based on the phase diagram that we talked about, second lecture? Volume of water plus volume of air, and then you have your volume of solids. Right. For a fully saturated system, how does that equation look like? Volume of water divided by volume of solids. All right. Now, what happens if I apply pressure at the top of the soil that is fully saturated? The magnitude of the stresses increase, right? We talked about the stress transference plots, right? Remember what the stress transference plots were? You apply the load, immediately you see an uptick of pore water pressure, and then with time, you see that the water drains from the medium, and therefore you see settlement will take place, right? So that's exactly what this equation here means. It means that the void ratio essentially changes, and that change is associated with the change in the volume of water, right? So in this case, what happens to the volume of solids? Quickly tell me what happens if I apply the load on this medium. Volume of solids would be, do you agree that it's going to be constant? The magnitude of the weight is going to be the same. What happens to the volume of water? Decreases, right? So it's not a sample inside the chamber in the lab. You're basically looking at the layer in the field. It's basically open on the sides, you apply the load and you see the water will drain. And what is that drainage a function of? The permeability of the soil, right? So if you're looking at clay materials, what kind of permeability do you expect from a clay material? Very low, right? Remember how you can define the permeability? Permeability has to do with the interconnected voids and therefore the path of seepage, essentially, right? The path of the water molecule that needs to travel within the medium. For a fine-grained material, that path is going to be a lot much longer compared to a open-graded material, right? So that's something that you might want to consider. So you have volume of water. What happens to the volume of water? And this decrease is a function of permeability of the soil. What happens to the void ratio? Denominator is constant, numerator goes down, therefore this will go down as well, right? So that's the reason that for the analysis of the settlement associated with the escape of water from the medium, we plot void ratio versus stresses, or effective stresses that we have. Log of sigma prime. Can you tell me how that curve should look like with increase in the magnitude of pressure at the top of the soil? As I apply more and more pressure at the top of the soil and let that loading conditions stay at the top of the soil, what happens? It basically will go down there. But this is going to be something like this. You're going to see two distinct slopes in that stress, in that void ratio versus log sigma prime curve there. And that's something that we're going to talk about that today, and that's going to be extremely, extremely important in terms of the settlement calculations. You have two slopes, two distinct slopes here. C sub r, or the rebound index, and C sub c, which is compression index. Alright, so let's see what we have here. This plot essentially tells me that if you increase the magnitude of the stresses up to a certain point, you see the decrease in the void ratio, right? But beyond a certain point, the structure of the soil breaks, and the rate of increase in the deformation is going to increase significantly with incremental increase in the magnitude of the stresses. So this basically means that the behavior on the two sides of this curve are going to be very different from one another. Essentially, you apply the load, the soil resists that, but beyond a certain point, the structure of the soil breaks, and you see settlement is going to be much higher compared to the other side. Right? So that's what this plot essentially tells you. And the idea is to develop this plot. And we're going to talk about how you can come up with this plot based on the one-dimensional consolidation test. So that's basically the objective of what we're talking about today. And we use these parameters to be able to do the settlement calculations. So let me recap of what we talked about here. We are interested in the time dependency of the settlement. Time-dependent settlement has to do with the dissipation of the pore water pressure from the medium. Dissipation of the pore water pressure is related to escape of water from the medium, drainage of water. We know that the drainage is different in different types of soil. We have clay material that it takes a whole lot longer for drainage to take place as opposed to a coarse grain material with big chunks of gaps in between, right? So that's basically the distinction between the two. We don't have the permeability right in here, but we are going to look at the after effect of that in the plot here. So how do we develop this plot? Based on a one-dimensional consolidation test. What are the things that we are interested in here? We are interested in two slopes, right? Because the behavior of the material is going to be very different on the left-hand side and the right-hand side of that plot. And also we want to figure out when that change in the structure of the material will take place, right? So for that, I need to also be able to figure out what that sigma prime naught is. That would be sub p. Remember in the first lecture, we talked about soils have memory. That sigma prime p is the memory of the soil. So what that means is that sigma prime p is called the pre-compression pressure. The implication of that is it's the maximum past pressure that the soil has ever experienced throughout its formation, millions of years. So you can identify what was the maximum stresses that this soil has ever experienced. So if you go back outside, go across the street, grab a bucket, put soil inside of that. This is in loose conditions, right? And then you go and compact it and run this test that we're going to talk about. You can figure out what was the maximum pressure that this soil has ever experienced in millions of years. And that's the memory of the soil, essentially. And that's a unique number. So now let's figure out how we can essentially find this. So,
if you had like a certain soil, but like say you had rocks, you know, and then but they were in the river, and then now you change the shape, you know, now you got rounded. So
yes, you're looking at the same behavior of the same material. Now you're changing the material. If you change the material by changing its geometry or changing its particle size, now it's a different type of mix. Right? So that's important, and that's actually a very good question. Therefore, this is more valid for fine-grained soils, not big chunks. We don't run that on the big chunks. Good one. For the big chunks, which one do you think is the predominant one in terms of the settlement of lines? Remember, we had the time-independent and time-dependent components. Now, for that case, dissipation of the pore water pressure is not going to be the determining factor. You have big chunks of aggregates, and you don't see much of a pore water pressure development inside that. You have pore water pressure, the surface tensional forces, and all the other things that we talked about. So that's not a player here. For that, immediate settlement is going to be the predominant factor. This one is more valid for fine-grained soils. Why? Because fine-grained soils has low permeability, and therefore it takes a long time. These are the operating rules. Long time dependency. It takes a long time for the water to drain, and therefore the settlement to take place. In fact, if you look at some of these clay materials, sometimes it takes several years for the ultimate settlement to take place. And we have techniques in the field to expedite the process of pore water dissipation. We'll have one case study that we're going to talk about that hopefully in our next section. And that would be coming from your part of the world, from Dubai. The big tower of Dubai that they built right in the middle of Persian Gulf. So it's fully saturated soil in the middle of water. How did they build the foundation right there and make sure that all those water is essentially dissipated from it? That would be interesting to look at. All right, getting back to our discussion about the audiometer or one-dimensional consolidation. Yes. All right, so let me just quickly recap of what we want to get from this plot. We want to figure out what are the sigma prime p, and that would be the maximum past pressure that the soil has ever experienced in its lifetime. Right? So that would be one parameter that I'm interested in. Now, there are two other things that I'm interested in. One would be the C sub C. We call that coefficient of compression or compression index. And then you have C sub R, or the rebound index, or the recompression index. You have all these definitions in the slides. You can take a look at that later on. But at this point, I just want you to grasp the general concept. All right, so let's see how we can run this consolidation test, or 1D consolidation test in general. All right. Remember you had your direct shear test. Remember you had a box. Now we have a ring here, right? So it's basically a ring, and you place the soil inside of that. Okay? Typically the soil is saturated. You go in at the bottom of the ocean and you extract the material. We'll talk about how you can extract the material without disturbance in the graduate level courses. And you place the material inside of that. You trim it. You make sure that you don't change the internal structure, because you know the internal structure, that void content, and interconnected void content, if you will, those are the ones that it determines the permeability of the soil. So you have to be very careful with the disturbance. Don't mess it up, don't recompact it, make sure that the sample that you source it from the bottom of the ocean, very well placed here, and you trim the around it. And you place it in here, and then the next step would be the loading. And you fill this one with water, right? So it's going to be full of water, meaning that the soil is fully saturated. Right? And you place the porous stone and the loading plate at the top of the soil right here. And this would be the mechanism that you apply the load. Right? You use different surcharges, different magnitude of the weights at the top of that to be able to control the magnitude of the stresses. Right? And you do it at multiple increments. We do it at, typically it's 10 points or 7 points. We're going to talk about that. So essentially what you do is you place a, let's say, a weight of 100 grams at the top, right? And let it sit for 24 hours. What happens? The soil is fully saturated, you apply the load based on the curve that you see right there. What happens to the void ratio? Goes down, right? Why? Because you see settlement. What is that settlement a function of? Fully saturated, there is no air in there, there is no compaction, if you will, right? Therefore, it's all going to be associated with the escape of water. How does the water escape? From the porous stone at the top and the porous stone at the bottom. Where does the water go? It goes to the water bath here. Right? So that was the first step. Place 100 grams at the top of that, wait for 24 hours, and monitor the deformation. How much this plate goes down. That would be your settlement, right? Settlement at the end of stage 1. Next step, double the load. Instead of 100 grams, put 200 grams. Wait for another 24 hours. What happens? It goes down. Look at the curve. The higher would be the magnitude of stress, the lower would be the void ratio, the higher would be the settlement. Next step, we had 200, now put 400. Every time we double the magnitude of load. Right? We do that 7 times. And we monitor when the structure of the soil will break. Right? When that change in the slope will take place. Also, once we finish the 7, after the 7th day, right, there are 7 stages, right? Every time we do it for 24 hours. And then we start removing the loads incrementally. Now, what happens here? Right, remember in the previous lecture we talked about the concept of swelling, right? We had consolidation, primary consolidation, and swelling behavior. That means that if you reduce the load, now the water gets into the body of the soil. Right? Now what happens? Void ratio increases, right? The volume of water would be going upwards. So we do it both for the loading and unloading, and we're going to talk about the behavior of the material, how it would look like, and how we can figure out what those parameters are. Right? So you figure out what the test is about. It's a 10-day test. Right? You basically start with the lowest magnitude of the surcharge, and the surcharge would be the weight that you place at the top of the saturated soil. It's saturated, meaning that volume of air is 0. Volume of water is what is determining the numerator of that void ratio, right? And by increasing the magnitude of the stresses, you see more and more settlement will develop in the system. Make sense? That's basically what the process is. The idea is to monitor or figure out 2 or 3 things based on that plot that you're going to generate. One would be the slope on the flatter side. The second one would be the slope on the sharper slope, right? And also you want to figure out what is the stress that the structure of the soil will break. We call that the pre-compression pressure, or the maximum stress that the soil has ever experienced throughout its formation. So that's basically the objective here, and then we use these 3 parameters to be able to do the calculations of the settlement.
You said it was 7 days or 10 days?
7 days loading, and then typically 3 days of unloading. We talk about why we need that unloading. The reason that we need the unloading part is that if if you start unload the material after, for instance, you reach this point, you see that the material starts to swell, and this slope is going to be exactly the same as the first. And that's the reason that they call it rebound index, or swell index, or recompression index as well. All of those starts with, the first two starts with R, and the second one with S. Right, so you might see C sub S as well, that C sub S and C sub R essentially synonymous. Alright, so let's get into the process of testing and doing the quick calculations of settlement of the soils. Alright, so this is my consolidometer that I showed you, or audiometer. An audiometer, as you can see, is consisted of a water bath, and this is your soil, and it is sandwiched between two porous stones. What this means is that the water can essentially either penetrate or escape through the top platen and bottom platen, right? These two porous stones that we have. All around it is going to be that metallic ring that we see there. The path of seepage is going to be important, so we will talk about that at some other time. All right, you place a sample here, and then you have the dial gauge and the mechanism that you apply the load. That dial gauge purpose is to monitor the deformation of the material. And we use this information to ultimately generate that famous plot. And the famous plot was void ratio versus log sigma 1. That's extremely important, right? It's log of effective stress. What's the significance of that? It means that it's not arithmetic, meaning that if you just misread the numbers, you might see it influence your calculation significantly. Similar to what we talked about in terms of the gradation curve. Remember gradation curve? What did you have on the y-axis? Percent passing, and on the x-axis you had log diameter, right? So that was exactly the same thing. So these are half logs, and the purpose of that is for the normalization, and so we can see the linear portions of the curves here. This is a description of the consolidation test that we talked about, and this is the process. This is the samples that is sourced from the bottom of the ocean. In this case, it's mentioned that it's coming from a Shelby tube, and that's one of the samplers that we have, that we send it down into the ocean to be able to get the samples there. You have the sample, then you have to trim it, as you can see there, to be able to fit it into the metallic ring, and you have it here. The idea and the part that you have to be extremely careful about is make sure that the sample is not disturbed. Right? The disturbance of the sample is important because that changes the permeability of your soil. And we know all these deformations or settlement associated with the primary consolidation is associated with the escape of water from the system, or permeability. Right? So you have to be very careful with that to make sure that you're not disturbing the sample.
Dr. Stern,
Yes.
you use the same sample through the whole test?
Yes, exactly. Yes, it has to be the same sample.
Wouldn't adding the weight disturb the nanotube,
It does. It does.
So then it
And in
changes.
reality, in the field, it does too, right? When you place a structure at the top of the soil, that also changes the permeability and the internal structure of the
So
soil.
you want it to hard.
Exactly. So you want to replicate what's in the field. That's actually a very good question. The idea of laboratory testing is to simulate the field conditions. That's the ultimate objective, right? If you load the material in a different way that they're going to experience it in the field, you basically get some parameters that are not going to be representative. So it's important to essentially look at the loading protocols. These are we have ASTM and OSHA standards for this, and these are very well written and documented. But if you want to look into some very special type of structures, the first step is to run some sort of numerical analysis to be able to figure out what the loading protocol should be. We call that stress path testing. Stress path testing has to do with the exact conditions of the stresses in the field that are going to be deviating from the typical ASTM or OSHA standards that you might have. Alright, so once you place the material, notice that you place this porous stone at the top of the soil, and you set the dial gauge to be able to monitor the magnitude of the stresses. And this is essentially what you see in your consolidometers. I'll suggest that you take a look at that when you go to the lab today and run your, assuming that you run the unconfined compressive strength test for today, but take a look at the consolidometer that we had in the lab as well. So essentially this is consisted of this the sampler that is inside of that, and you apply the loads. And this is going to be a typical loading conditions that we have. You do have the information about the temperature, which is essentially constant for our case. And notice that what we have here, this is the vertical distresses in terms of the kPa. And notice that each step is essentially double, right? So you have the 100 kPa, the next one would be 200 kPa, the next one would be 400 kPa, because you want to see the deformations in the material. And then you go backwards, right? You basically incrementally remove the loads to be able to see the swelling behavior, right? So that's basically the objective of running the consolidation curve. And this is the curve that you end up getting. You see, if up to a certain point you have slope, we call that C sub R, and then after another point, you see that quickly the structure of the soil breaks, sharp decrease in the void ratio, which is synonymous with the sharp increase in the settlement of the soil. And then if you incrementally remove the stresses, you're going this way, meaning that the stresses becomes smaller.